Okay, we're going to do some problems from 5.4, and we're going to start by doing some derivatives using the fundamental theorem. So I've got this function here, h of x, and I want to take its derivative, and the fundamental theorem says that if that limit of integration on the top, if that had just been x, then h prime would be the integrand, which is arctan. However, we have 1 over x, so think of g of x as in the theorem as the thing you really want, which is 2 to x arctan t dt. And so that's composed with another function 1 over x, right? We'll call that f of x. That means that h of x is g of f of x. Well, then I can take the derivative using the chain rule. So it's g prime f of x times f prime of x. And those I can get from the fundamental theorem for g. So g prime is arctan using the fundamental theorem. And f prime, just using derivative rules, is minus 1 over x squared. So applying those here, this is arctan of 1 over x times minus 1 over x squared. And that is h prime right there. Now we're going to add some integral rules to this, and we're going to tackle 14 here. So this is the integral from sine x to cosine x of 1 plus v squared all to the 10th dv. So they call this y, and they want to find y prime. Well, the fundamental theorem doesn't quite apply, neither does the chain rule trick, so let's pretend that there's some number between sine x and cosine x, or maybe they're the same number, but either way, then we just use that one. And we're going to rewrite y as sine x to a, and we don't necessarily care what a is, just a constant. And then it's going to go from a to cosine x. So that's one of the integral properties that we have. And now the fundamental theorem needs the function of x to be on the top. So this is then minus a to sine x using another rule of integrals. And then this is a to cosine x. So now we can use the fundamental theorem together with the chain rule. So let's do that on the next slide. We'll do a and b separately here. So a here was the negative of the integral from a to sine x. 1 plus v squared to the 10th dv. So if I take a prime, using the chain rule like we did in the previous example, this is without the negative, and then it's 1 plus sine x instead of v squared to the 10th times the derivative of sine, which is cosine x. And then for the second, this was a to cosine 1 plus v squared all to the 10th dv. We're going to basically do the same thing. This is going to be 1 plus cosine squared x to the 10th times the derivative of cosine, which is negative sine x. So when I add those together, I get y prime is equal to negative cosine x, 1 plus sine squared x to the 10th minus sine x, 1 plus cosine squared x to the 10th. And that right there is your answer. So now what I want to do is move on to some applications with average value. So this is number 19 in 5.4. And I first want you to find the average value of f on the given interval. So this is f of x equals x minus 3 squared on 2 to 5. So to get that, remember f average is 1 over b minus a, where that's the limits of integration from a to b, f of x dx. So you divide by the width of the interval after you integrate. So in this case, that is 1 over 5 minus 2, integral from 2 to 5, x minus 3 squared dx. Now, we don't have a rule for products, so we need to expand that. So it's 1/3 times the integral from 2 to 5, x squared minus 6x plus 9 dx. Now I can use the power rule. So it's x cubed over 3 minus 3x squared plus 9x. First plug in 5 and then plug in 2. Then I need to evaluate that, and you should get 1 as your final answer. So the average value here on this interval is 1. Well, part B says to find C such that f of C is equal to f average, which is 1. And this is guaranteed to happen by the mean value theorem for integrals, which is the last part of this section. So we want to figure out where x minus 3 squared is equal to 1 within that interval. So if I take the square root of both sides here, since I'm already in that form, I get plus or minus 1. So then x is 3 plus or minus 1, so it's 2 or 4. So those actually both happen in the interval, so there are actually 2 instances where you hit the average value. The last part is to sketch the graph of f in a rectangle whose area is the same as the area under the graph of f. So let's see if I can do that carefully. So f is just x squared shifted so that the vertex happens when x is 3. So let's try to get some graph paper here. The x is over here. So at 3, here's my vertex. So I guess it should look like this. Forgive the squiggles. And I'm going from 2 to 5. So it's just to be this region. So I want it to be the same as the area under the graph of f, and so the area was divided by 3 to get the average value, so the area should be 3 units. So if I take a rectangle that's, I guess, 1 down and 3 across, I may have goofed a bit at 5 here. But no, that's about right. So those don't look like the same area, so you have to forgive my artistic skills, but we know that the area was 3 based off part A.